I'm Ovidiu Petridean. I work at SDL. Yes, it does say development manager, but I do write code. So basically, everything I'm going to talk about is hands-on experience with what we've been through in the past 5 years or so, with our migration from a monolithic system to a microservices system from a data perspective. So basically, 5 years ago, we had a really, really cool API. It was able to handle lots of translations, lots of transactions, and everything was running really fine. But then, in the machine translation industry where we operate, things started to change, and everybody started to move from the statistical machine translation models to basically models that are based on neural technologies. And trying to move from that to something new proved to be a bit difficult in our old model. Therefore, we looked around and saw, okay, what can we do? How can we improve? And the choice was to move to microservices. Of course, these presented with challenges, and I'll try to look at some of them from a data perspective. Basically, I'll just a couple of slides about microservices, just some key points, then a bit about the data types that we handle, some patterns that we used in order to handle the different data types that are within the system, and some technologies that we are using at SDL to handle all this data. So about microservices, how many people here use microservices? How many of you do it in a production environment? And how many of you migrated from a monolith? Okay, so just a few. We're kind of in the story where we migrated from the monolith without trying to actually convert the code, but writing everything from scratch. Just keeping the business capabilities similar to what we had before. So basically, a few key points here. Microservices are just an architectural style. That's it, that's how we looked at them. And an application is viewed as a collection of services. For example, for our platform, we have over 50 services that are divided between 3 products. And a subset of those services is used for all the products, and some others are basically just business specific for each of the products. The services have to be highly maintainable and testable, and that's definitely a key requirement. They also have to be loosely coupled. That's also a super important requirement, because you need to be able to reuse the services, and you need to be able to work independently on the services. They also have to be independently deployable, because let's face it, if you deploy the microservices at once, you're just basically deploying a monolith. Been there, done that. But we learn from that, and now we have this setup. They also have to be scalable. That's one of the powerful things about microservices, is that you can scale individual parts, individual components of your application in order to achieve better throughput, latency, or whatever you're trying to achieve, and on whatever you're trying to scale. And as I said, we have around 50 services that are organized and that are being used by 3 different products, 3 different products, and 3 different teams. And those services are organized around business capabilities. So we have some core services that are shared, but the others are really organized around business capabilities. Now, let's look at this from a data perspective. So I said an application is just a collection of services. Of course, the application uses data. They have to be highly maintainable and testable, Well, yes, because you will change data, you will change data structure, you will evolve the architecture. They have to be loosely coupled. Absolutely, everybody has to own their data in order to achieve this, because if you're sharing data, you cannot really have loose coupling. Do they have to be independently deployable? Also implies that you need to own the data. Scalable, the same thing. Data has to be independent in order to be able to scale. Do you just need to scale your, I don't know, account management part of the application? Sure, maybe you just need to scale some SQL database. There's no need to touch any of the NoSQL databases or anything else you have in the system. And of course, looking at the business capabilities, one of the requirements that we had was to also have data protection in place. This is basically one of the key components. So SDL is one of the third large machine scale translation provider after Google and Microsoft. The key differentiator is that we provide data security. We will not share your data. So this was a key requirement for us to try to do any kind of data protection that's needed. Now, we looked at microservices, and we looked at how data impacts the key characteristics of microservices. Now, let's look at what kind of data types do we have when we talk about an application that uses the microservices architecture, but not only. I mean, this is the case for other applications as well. We have data at rest, and we have data in flight. Those are the two. This is a way to look at data. So when we look at data at rest, we think of databases, we think of disks, we think of anything that's a persistent storage that can hold data that may or may not be used at some point. However, when we look at data in flight, we're talking about data that's moving through the system. You have requests, you have communication between services. All this is data in flight. It's data that's being moved between services. Of course, at any point, data at rest can become data in flight when you just query databases. When you query databases, or when you do any kind of, when you have any kind of interactions in which you move that data around between microservices. So basically, for data at rest, we have some requirements. One of them is that it has to be highly available. And at first, we thought it's fine to design a system where some of the transactions can be lost because the client will just restart the transaction. We thought, well, these translations is not launching spaceships or anything like that, so the client will just resume it. However, that wasn't the case for an enterprise customers. They're really paranoid about data, so we could not really afford to lose any data. And then the other challenge that we had was, okay, how can you have zero downtime scaling without losing any of your, of course you cannot lose any of the at-rest data, but this is also important for the in-flight data. You cannot lose any in-flight data when you scale. So this was another challenge. Then I said the data had to be protected, and this ties in with encryption, with password protecting, with data center protection, and anything else that can be engineered, like the way you access the data. We run multiple times, we run pen tests just to check that our application is secure, and basically the target is always the data. We have internal pen tests, we have external pen tests that are being run just to try to see if the data is protected. This is this is the most important thing for our customers, to ensure data protection. When you have large companies that are translating sensitive content, you don't want that shared with any third parties. The data is also stored physically, and stored physically means either using file systems or various types of databases, and the data has to be backed up in order to prevent any kind of data loss. I mean, who in here has ever deleted a table or a database in production? Nobody? Just me? Okay, a few of you. So it happens. So you need to make sure that you have backups for your at-rest data in order to restore whatever happens when you, in order to restore data that is being lost for various reasons. Then you have in-flight data. And for in-flight data, you have external data, and in our case, those are the requests that are coming from our customers. Most of our customers interact with us using the APIs we provide. So this is the entry point in our system, is an API call. Then it reaches the endpoints, which are just a set of services in our case, where you have to decrypt the data, you have to authorize, you have to make sure that the calls are legit. Then you have business services, and you have inter-service communication, which in our case means that once the data hit the endpoints, it will start flowing through different business services in order to do whatever operation is needed. But then, from the business services, it hits our data services. I'll talk about it in a bit more detail a bit later, but basically we have split the business services from the data owner services. And then the data owner services will eventually persist the data. That's not true for all the data, but that stands true for most of the data. Okay, so we have the microservices. We have some challenges, we have some key points. Then we saw that there is at-rest data and in-flight data. Now, we looked at all this, and at first it seemed, well, it shouldn't be a big deal. I mean, we've been doing this for a few years. It should be fairly straightforward. However, when we started to implement it, the first thing we did was to do something which was really close to our monolithical approach. And then we started looking at different data patterns just to see, okay, how can you evolve that architecture from something that's really close to the monolithical world, which has its positive things and its drawbacks. But when we decided that we want to move away from that, we also had to adopt a new way of handling data. So let's look first at data requirements. I've been through some of the requirements in the previous slides, but let's look a bit at this. So there are some things which are really, really, really easy to achieve in a monolithical world, because things have been in place for that kind of an approach for lots of years. You have transactions, you have all those things that are just there. However, in the microservices world, if you want to do it the right way, if you really want to go, and if you really want to have all those points that I made before, where services have to be scalable, have to be loosely coupled, and so on, you'll have to divide the ownership of the data between services. And when you do that, you will lose some really simple capacities, like how do you do joins when you have separate services? How do you do transactions when you have separate services? This is also really, really easy when everything is in one place. But when things are shared and you have multiple services and multiple databases, things are not so easy. Yeah, so the requirements was to have loosely coupled services. Then you will have to have transactions. You still need to have transactions, even if you're doing microservices. So transactions will have to span now multiple services instead of just one. Data is owned by multiple services. You'll have to join data from multiple services. You won't get anything for free like you did in the monolithical approach. Then you'll have to have replication as well. You'll have to have sharding. You'll have to be able to scale. And you might have different requirements for different services. You might want to use SQL databases for some of your flows, NoSQL for others. And even for the SQL databases, you might want to use different things, different solutions. You might want to go with MySQL, or you might have a service that's written in .NET that uses whatever, SQL server or something like that. So you'll have to be able to handle that as well. Now, there are a few patterns that have emerged over the past years. I'm a big fan of Chris Richardson and its microservices.io website. Do any of you know that? So I really encourage you to look at his website. He's really, really good at doing architecture and providing different types of patterns for different challenges in the microservices world. So basically, we will talk about different patterns, and I'll share with you what we are using and what we have evolved from. One of them is shared database, where basically all your services share the same database. Another one is to have a database per service. Another one is something called a saga, and we'll look into details in a bit. And then you can have API composition. Basically, saga, API composition, CQRS, and event sourcing are all of them are different patterns to handle transactions, queries, data consistency when using the database per service model. So, just to go in details, when you have a shared database, is like the classic way of having just one database for all your services. Everybody will be able to access that data. You don't need to worry about transactions or anything like that. So you will have separate services, but everybody will be connecting to the same data source. Sure. And you have these benefits. You have AC transactions, and they are familiar, they are straightforward. So it's fairly easy. However, the challenges here are you have development time coupling, because when you have microservices, in the ideal world, you can have one team handling one or just a couple of microservices. It's not the case for us. However, we do have separate teams handling a subset of microservices. So if everybody has to do a sync up when changing any kind of data structures, you can imagine how this becomes a bottleneck, especially considering that our teams are spread across 2-3 time zones. So it's not that easy to use something like this. And then you have the storage and access requirements, which might not be satisfied. As I said, you might want to develop something. It is the case for us. Lots of our core NLP services are developed in Python. Then we have everything else which is developed in Java. However, the parts of the services that are developed in Python, if they want to use any kind of data, they might not want to use MySQL or HBase or whatever else. They might find something else that's suitable for their needs. And this is definitely a challenge here because you cannot satisfy the storage requirements for everybody by using just one or two types of databases without having all these kind of issues. So the first thing so we started with that shared database thing, and then we had all these issues. We couldn't change the schema. When you change the schema, you would have downtime, and that was not ideal. That felt a lot like the old way of doing things, but with new challenges. So we couldn't see the benefits. So then we started, okay, let's move to a database per service approach. So what we did was, was that we have basically, in a simplistic view, we have two types of services, caller services and services that are data owners. Services that are data owners, they are the only one who can touch a certain database. And the other services that are calling those services are just interacting through them, with them through an API. Now, the database per service approach looks something like this. You can have, I don't know, some order API, some invoice API. And as you can see, those services own their databases. And you have, sure, the data is persistent, it's only accessible through API. And for relational databases, you have three options. One of them is to have a private table per service. Another one is to have schema per service. And another one is to have database per service. Database server per service. We looked at all this and we said, okay, private tables per service, it's simplistic, but it's also kind of dangerous because you might get tempted at some point to say, okay, so just this database, I would share it between two services. Everything else is fine, but just this one, I really need to share it between services. And it's easy because everything is in one place. So it's really tempting to do these kind of things. So in order to avoid that, we looked at the other two options. Database server per service seemed a bit too much for our use case. The load was not so high that the load on the databases was not so high, so we didn't feel the need to have different services for each, different servers for each service. So we went with schema per service, which basically means that we have one set of servers that handles all the schemas. But every service can only access its own schema. Every service owns one schema. Services cannot own multiple schemas so this is basically just a one-to-one relationship between the schema and the service. Now, sure, you have these benefits. You have this coupling. You have various databases. I mean, if you look back at this one can be MySQL, this one can be something else. It doesn't really matter. So you have these benefits. However, you also have these challenges. Transactions will have to span multiple services. Joins will have to happen in multiple services. And you'll have to manage multiple SQL and non-SQL databases. This is mostly, the last thing is mostly true when you have multiple servers. But all these challenges are there. So, what are the solutions? The solutions is to use this database per service pattern, but combine it with one of these other patterns as well. API composition, command query responsibility segregation, and sagas. All this is needed to solve the challenges that I presented before, which is joins across different services, transactions, and so on. So, looking at Saga, basically, Saga is just a sequence of local transactions. So, when you have when you have, when this, basically what happens is that if you have a user and an account, and you have to update something on the account, but that also has to reflect on the user entity, you will have to first update the account database and then update the user database. How do you do that? To make sure that if something fails, you don't have inconsistent data. So what happens with Saga is that basically you will just update one database and then you'll have local transactions. You will update the account database and then you'll move to the user database and you'll update the user database. So this is what happens with the Saga. However, what happens when a transaction fails? So you have all these local transactions, that's fine. What happens if the transaction fails? So you update the account, but you fail to update the user. Then you have to do a rollback, which again, is really easy when you only have one database and everything is shared. You just start the transaction, do everything, and if not, the transaction will just roll back. That's not the case here. So how can you fix that? You will have to do compensating transactions. You'll have to undo the changes. You updated the account, you fail to update the user, you go back to the account and revert whatever you changed there, and just fail the whole thing. So this is the approach that Saga uses. Sorry. Okay. Now, the benefits are that definitely the data is consistent. As long as you make sure that if something fails, you will just roll back the other transactions, data is consistent. And you don't need to have distributed transactions. You can just have all these local transactions, and they will take care of everything, of updating everything. However, this is a complex programming model, and you have to design all these local transactions. So you not only have to design the transactions that update the entities, but you also have to design the compensating transactions that will do the rollbacks if needed. And the most important thing is that even if everything is successful, you have to do a two-step operation. And that is, you update the database and you send the event for the next service to update its database, and send the event for the next service to update the database. And that one sends an event saying, I'm done, everything is okay. So you'll have to do these two operations. And it might seem that, yeah, sure, you just do two operations. You update the database and send an event. But what happens if you update the database but fail to send the event? How can you do that atomically? And the answer is event source. And here, the programming model is a bit more complicated than we've seen with Sagas. So as I said, the need is to atomically update the database and publish the message. What event sourcing does is that it will persist the state of a business entity as a sequence of state-changing events. So you will have a service will persist this in a table, but you will also have something called an event store where you will just publish all these, state-changing events. And sure, if you go to the event store, you can just replay all this and say, first the order got created and my entity looked like this, then it got approved and the entity looked like this. So you can reconstruct the entire flow. And then you'll have all these services which are just subscribing to the changes. So in our model, you will update the account. The account will say, okay, I updated my state. And the user service will subscribe to events and say, oh, the account got updated. Let me get that, let me see how the entity looks like, and based on that, I will do this and that. So in this case, you atomically, this is the improvement, you will atomically both persist the entity and have this persisted in the event store, because this can be done in a transaction, in a local transaction. But then, subscribers will just look at the changes, and based on that, they will act. So yeah, sure, loosely coupled entities that exchange events. That's the core thing. And then, and then you can have the state of an entity at any point. Because of that event store, you can just query the event store and have what's the state of the entity at any point. However, there are challenges here as well. First of all, it's an unfamiliar style of programming, having to persist this extra thing, not just the entity. And then it might prove to be a bit difficult to store to query the event store. So when we looked at this, we said, okay, we should probably not go with this, because it is a bit too complicated. The fix for this, the next pattern, is CQRS. Basically what you do here is that you maintain a view of the data. So you still have your services that own the data, but you also maintain a view of that data. So for example, you have to update the account and the user, and your queries will fetch the user entity together with some account information. When you do that, you'll normally have to hit two services. What happens here is that you create a view which will get updated when something changes in one of the entities. So if you go back to the previous thing, you will update the account, you will update the user, and a service that listens to all these changes will update a view. So whenever you query, you will just query on this view. And with this, this view is read-only. So this will be a read-only database. Services still own their data. They are the only ones, the owners are the only ones who can change the data. But this view will allow you, will give you a read-only version of the data based on the queries that you're trying to do. So here, if you want to get the user with the account information, you will just query the view. You will construct a view that will handle that query. And of course that's really good, because it will prove to be really fast. You can optimize the views for the kind of queries that you need. But then, so you do have all these benefits, and it's simpler. It's pretty simple to do. So we fixed the querying part. The querying part is no longer something difficult that has to go to multiple services. You will just go to this view. However, you might have some code duplication, because you might have similar views. So you might have to create similar views. You will definitely have a replication lag. All those services will have to subscribe to events and update the views, but that will introduce some lag, whatever kind of system you're using to send the events. And of course, this will increase the complexity, because now you have the database owners, then you have these view owners, and then you have your services that query the views. And writing the data still happens on the database owners levels. So you have to interact with two entities. So we looked at this as well, and we said, yeah, this is still a bit too complicated and too complex for our use case. So now the next pattern is what we chose, and it's called API composition. So what happens is that you no longer have any event stores, you don't have any views, you don't have anything, you just have database owners, that's it. But whenever you want to query data, you will have to query it by using all those services. So if I want my users and account, I'll have to query the account owner and then the user owner. And then I will do the join in memory on the caller service, on the service that actually needs the data. Of course, this has the benefits that you no longer have to maintain any other data structures. And it's simple to query the data. You just query everything and join everything in memory in any way you need it. But it can definitely prove to be inefficient if you have large queries. We have successfully used this model because we were smart about the way we do the queries, and we only try to fetch the minimum amount of required data in order to do those joins in memory and present the data to other services or to customers. Okay, so with all those patterns, we started from a shared database, we went to a database per service, we looked at different things to solve the challenges there, and we said, okay, database per service and API composition is good enough for our needs. Now, we started looking at the technologies. We kind of looked at technologies, which I think it's sometimes a common mistake. When you have a problem, you don't really look at patterns on how to solve that problem, but the first thing you will think, okay, I can solve this thing with Kafka or with MySQL or with whatever. And that's fine. But then, if you need to change anything, you'll have to make sure that the patterns will have to suit whatever technologies you have. So in terms of technologies, we were one of the, we'll look at technologies from an in-flight data perspective and an at-rest data perspective. So we started with the popular Apache Kafka. Back in 2014, this was software that was at version 0.7. So we kind of took a leap of faith, saying that, yeah, Kafka looks like a good tool, and it will probably do the job for our in-flight data. And we had a success story with Kafka. We use it to communicate between our services. So all our service-to-service communication happens through Kafka. All the messages that are being exchanged between services happens through Kafka. And that was cool because the other option that was popular was to use HTTP calls between services. But then you have to do service discovery, you'll have to see how to handle throughput. HTTP calls are not as light as TCP, what Kafka uses. I don't want to get necessarily into details, but those are one of the main reasons why we went with Kafka. So all the services communicate through Kafka. However, we discovered probably a couple of years later or so, when we had the first really large message that had to go through Kafka, that it just failed. And it's not just that it failed, it silently failed. So we had no idea what's happening. But basically, with the default settings, you couldn't really transport more than 1 megabyte of data. So that was a challenge. The other thing is that you always have to be careful about how do you design your topics and partitioning strategy. Just to give you a quick example, we thought it would be a really cool idea for every service to have a set of partitions, and then whenever you scale, if you need, you just create new partitions and so on, so that you don't have lots of partitions pre-created. Kind of a bad idea. Then you'll have to challenge. You'll have to do the deployments, no downtime, blue-green deployments. Not so easy when you're using Kafka as a tool to communicate between microservices. So, in order to fix that 1 megabyte challenge was, okay, how can we transport data between two services when you have more than 1 megabyte of data? Sure, you can tweak the chain, you can tweak the settings and all that, but Kafka behaves poorly when you have large data. It was not designed for that, basically. So we had two options. One of them was to do data chunking and just say, okay, this data will get chunked in, I don't know, 100 kilobytes messages, and all of them will be sent. You'll have to add some sequence number to all of them, and the service that gets all this data will have to recompose everything, put everything together and say, okay, this is how the message looks like. But there might be challenges there as well, because some data might prove difficult to split, and then you'll have to see, okay, what happens if you have any message loss. So there are some challenges there. So we went with the other approach, which is to use a persistent store. In our case, the persistent store was HBase. So the flow is like, you get a message. If the message is of a certain amount of, it has a certain size, you will persist the message and just send the reference to the next service. And the next service, based on that reference, will just get the data from the persistent store. So this was the, let's say, hybrid approach that we took. And this one has these benefits, that it basically has the same benefits as Kafka, and it will also take care of that disadvantage with the large messages. But it also has some complexities. So you will have more complex flows, because you always have to do this if-else thing. If the message is larger than this, go to the persistent store. If not, just send it as it is. It adds another dependency. In our case, HBase was already in the stack, so it was pretty easy. But if you don't have that, you will have to add a persistent store. That can be anything. That can be the disk if that's simpler. And doing dealing with eventually consistent databases presents challenges, because this service will say this message is large, I'll persist it and just send a reference. However, because HBase is eventually persistent, you will get the message, you'll get the reference, but that reference might prove that, the message might not be persistent when you get the reference. So you try to query something, but the message is not there. Which kind of brings us back to one of the patterns, which said that you have to atomically do the persistence and send the message. What about at-rest data? So our stack uses this. Our stack is composed of this. These are just some of them. So basically we use HBase for large data, for everything that's not relational. Then we use MySQL for relational data. We use Elasticsearch for anything that's logs, statistics, and HDFS for whenever we need to archive data or to keep data that we only perform some analysis on. Cool. I still have 1 minute, so just a quick recap. We looked at microservices, we looked at the architectural style, we looked at the key points, we looked at data types, at rest and in flight. We looked at the patterns, shared database, database per service, and every other pattern that was helping the database per service pattern to achieve everything that's needed. And then we look at the technologies for both in-flight data and at-rest data. And I guess that's pretty much it. Thank you.